Welcome to section 6-8, Rotary Motion. At the end of this section, we should be able to answer these questions. What is angular velocity? What is linear velocity when working with rotary motion? What is the notation we will use for the various concepts in rotary motion? What is the formula for angular velocity? What is the formula for linear velocity? And how do we use these formulas to analyze the motion of rotating objects? So what's the big deal about rotary motion? Well, let's see what Calvin thinks of it. Here's a nice little strip. Dad says, playing a record? I'll show you something interesting. Compare a point on the label with a point on the record's outer edge. They both make a complete circle in the same amount of time, right? Calvin, yeah. But the point on the record's edge has to make a bigger circle in the same time, so it goes faster. See, the 2 points on one disk move at 2 speeds, even though they both make the same revolutions per minute. Mind blown. Let's clarify some notation before we really start discussing the ideas of rotary motion. So first of all, we're dealing with a circle. So one of the things we're going to need to talk about is its radius. The radius we will simply call r. From the center of rotation to whatever point we're talking about that is demonstrating this rotary motion. A will stand for the arc length, or the distance around the circle that the object is traveling. So the number of units of arc length through which the point moves. Theta, as you can see here, will be the angle through which the point rotates. Usually we'll measure it in radians, but not always. This sign, the V, is going to stand for the linear velocity in distance per unit of time. So that's the linear velocity. This fancy W is also known as an omega, lowercase omega, and that will stand for the angular velocity, which often we measure in radians per unit of time, but it doesn't have to be radians. It's the Greek omega. And then T will stand for the length of time that we're using to measure this rotation through a particular angle. Okay? So now that we have our notation down, let's talk about some of the ideas. The angular velocity of a point on a rotating object is the number of degrees, either in radians or revolutions or so on, could be any of those, through which the point turns per unit of time. So basically how far around a circle, what proportion of a circle have we traveled around? And we'll use again the omega symbol there to discuss angular velocity. The linear velocity of a point on a rotating object is the distance the point travels along the path per unit of time. So not what angle did it cover, but the actual distance around the circumference of its circular path. And we'll use V there. Now notice these are both velocities, so they're both measured in change in something over time. So our omega, or angular velocity, is change in degrees over time, where our linear velocity is simply going to be the arc length over time. So linear velocity and angular velocity are related. If we measure our angle, theta, in radians, and omega is in radians per unit of time, then we can say that our arc length is our radius times the angle measured in radians. We discussed this in an earlier section. Our linear velocity will be our radius times the angular velocity. So linear velocity is radius times angular velocity.